Hello everyone. Today we are going to discuss the topic that is organic reactive intermediates. So basically this topic is going to be useful for the MSc1 chemistry students and also for the students who are preparing for the competitive examinations like NET set or GATE examinations. So this video is going to be introductory type or just basic type of video. So we will start this topic, that is our organic reactive intermediate. So basically when an organic reaction or any other reaction occurs, in that reaction the reactant reacts with the reagent to give a product, but the reagent and reactant reacts and directly does not give the product. There is a state between the formation of product and the starting compound. That state is known as intermediate state. So intermediate is the state, or intermediate is the short-lived species formed during the course of any reaction. So in a chemistry, a reactive intermediate is a short-lived, high energy, high reactive molecule. Okay, so these species are short-lived species. If the species is short-lived, it means that it has high energy, and if the molecule has very high energy, then the molecule is highly reactive. So when an intermediate is generated in a chemical reaction, it will quickly convert into more stable molecule. So why it convert into more stable molecule? Because we know that it is a high energy molecule or highly reactive molecule. So highly reactive molecule tries to attain a stable compound or stabilization. So this, to attain a stable compound or stabilization, it will quickly convert into a more stable molecule. So these intermediates are these intermediates are short-lived, so it is not possible for every time to trap them, but only in exceptional cases these compounds can be isolated and stored. When their existence is indicated, a reactive intermediate can help in explain how a chemical reaction takes place. So when a chemical reaction takes place, the starting compound reacts with the reagent to give the product, but this is not the one direction process, or it does not occur in a straight way. So the starting compound undergoes some changes, and this changes will form the product. So when an intermediate is trapped, it can give us information about how the reaction occurs. So basically, we are going to discuss in this chapter the reactive intermediates which involves carbon species. So the carbon species which involves intermediates are carbon free radicals, carbenes, carbocations, carbanions, nitrenes, and benzynes. So let's discuss about the main carbon reactive intermediates. This is carbocations, carbanions, carbenes, free radicals, and nitrogen. So basically, when a compound reacts with reagent, there is the formation of new bonds and breaking of the old bonds. When the bonds are break, there are two types of bond breaking, that is heterolytic cleavage and homolytic cleavage. When the bonds break heterolytically, there is a formation of positive and negative charges, and when the bonds break homolytically, there is formation of free radicals. So carbocations and carbanions are formed by heterolytic cleavage of the bond, and carbenes, free radicals, and nitrogens are formed by the homolytic cleavage of the bond. So we will discuss one by one. So first is carbocations. So carbocations, it is also known as carbonium ions. So organic ions which contains a positively charged atom are called as carbocations, or organic ions which contains a positively charged atom are called as carbocation or carbonium ions. So carbocation is further classified into two types, that is carbanium ion, that is trivalent positive species, here CH3 plus and C2H5 plus. So these species are carbanium ion, and yeah, they are also known as classical carbocation. They are also known as classical carbocations. And other type is carbonium ion, where it's pentavalent positive species. It is known as non-classical carbocations. Here you can see that the structure of a carbocation. Here you can see that the bonded atoms are at 120 degree, and this vacant orbital is perpendicular to the carbocation. So structure of carbocation, basically it has been experimentally found that the carbocations are trigonal planar around the carbon bearing a positive charge. The structure is trigonal planar. If the molecule is trigonal planar, obviously their hybridization is going to be sp2 hybridization. Now valence bond theory as well as molecular orbital theory easily accounted for such structure. It is more comfortable to discuss the valence bond approach. The carbon with the positive charge is in sp2 hybridization with 3 hybrid orbitals oriented at 120 degree, okay, in a plane with an empty pz orbital perpendicular. Here you can see that this is empty pz orbital which is perpendicular to the carbocation, and these bonds are the bonded atoms are at 120 degree away from each other. So here you have to remember that it is a trigonal planar species. Why? Because hybridization is sp2. Okay. Now here one thing you should also remember that it is a 6 electron species. It has 6 electrons. It is a 6 electron species. The order of stability of carbonium ions. Now, the carbocations are stable according to the or various factors effects on the stability of the carbocations, in which out of which the first factor is inductive effect. So here you can see that tertiary carbocation is more stable than secondary. Secondary is more stable than primary, and primary is more stable than methyl. So why this happens? Because this carbocation is a electron deficient species. So it is an electron deficient species. If an electron deficient species is attached to the electron donating species, then the carbocation will be more stable. Here you can see that these CH3 groups are plus I groups. This CH3 group shows plus I effect. Here you can see that there are three CH3 groups attached to the carbocation or carbon containing positive charge. So these three plus I donating groups increase the stability or in donates electron to the positive charge. So it makes more stable to it. Here only two CH3 groups are present. Here is one and here is no CH3 group. So the stability will increase as the electron donating groups increases or the attached electron donating groups increases. Okay. So next case is the second case is of unsaturated carbocations, where the carbon bearing positive charge is directly connected to carbon participating in multiple bond. Here you can see that this is allyl carbocation. This is a allyl carbocation. Where here this double bond will participate in resonance with the positive charge, which makes the carbocation more stable. Here benzyl carbocation. Here the double bonds present in the ring will participate in the resonance with the positive charge to make it more stable. Here diphenyl methyl carbocation. Here two phenyl rings are present and this is a carbocation. Here two phenyl rings gives their plus I or plus R effect to make this carbocation more stable. Here three phenyl rings are present. As the number of phenyl rings increases, the stability of the carbocation will also increases. As the number of phenyl ring increases, the stability of carbocation also increases. Since the carbon in carbocations has only 6 electrons, it is electron deficient species. As earlier I have discussed with you, it is a 6 electron species, and you know that carbon's valency is carbon's octet is a carbon's octet needs 8 electrons in it to it make it stable. So here is only 6 electrons. So 6 electrons is there, hence 2 electrons are here deficient. It is an electron deficient species, and therefore any effect that can compensate for the deficiency will stabilize the carbocations. Means what they want, what they are saying, if there is a deficiency of electrons and someone is giving electrons, so when someone is giving electrons and the deficient species will accept that electrons, if the number of donating electrons or number of electron giving species increases, the stability of the electron accepting species also increases. So therefore when plus I or plus R donating plus I or plus R effect showing groups are attached to the carbocation, then the stability of the carbocation increases. Here you also see that resonance stabilization. Now as the number of phenyl groups attached to carbon bearing positive charge increases, the number of resonating structures will also increases, and the resonance structure increases means the stability of the carbocations also increases. Now we have discussed about the structure and the formation of structure and the stability of the carbocations. Now we will discuss how the carbocations are generated. So earlier I have told you that when a reaction occurs, there are two types of bond breaking, that is heterolytic cleavage and homolytic cleavage. Here carbocations and carbanions are formed by the heterolytic cleavage of the covalent bond. So the heterolytic cleavage of the covalent bond is responsible for the generation of most of the carbocation species. Some of the reactions involving the production of carbocations are given. First is ionization of alkyl halides in polar solvents. So the polar solvents, when polar solvents are reacted with alkyl halides, the polar solvent will abstract chlorine group from the alkyl halides, and if this chlorine group are detached from this alkyl halide, it will give positive charge on this alkyl group. So here is the formation of carbocation occurs. Here is heterolytic cleavage of the bond. The chlorine depart from this group by taking electrons from this bond. So this bond gets positive charge. Second is protonation of alcohols followed by dehydration. Now protonation of alcohols. Protonation of alcohols by followed by the dehydration. Okay. Okay. So protonation of alcohols means what? When alcohol is treated with any acid or H proton source, this alcohol will, the lone pair of the alcohol will abstract this proton, and after abstracting this proton, it will form a species that is OH2 plus, which is a good living group. That is, dehydration will occurs easily, and after dehydration, this carbocation will be formed. After dehydration of the species, carbocation is formed. The third method is protonation of unsaturated system. So unsaturated system means system containing double or triple bonds. So double or triple bonds are nucleophilic in nature. So they have tendency to give their electrons to electron deficient species. Here you can see that this double bond attacks on this proton. So this proton double bond gives electrons to this proton, and there is a formation of the bond between these protons. Okay, and here the double bond gives electrons. So therefore this carbon becomes electron deficient. Here you can see that the formation of carbocation on this carbon. Fourth is action of superacids on alkyl chlorides. So superacids reacts with alkyl chlorides to give carbocation. Next, deamination of primary aliphatic amines by nitrous acid. So nitrous acid is used for the deamination of primary aliphatic amines. So aliphatic and aromatic amines, you should know the difference between them. So here, this is primary aliphatic amine, and this is nitrous acid. It will form this intermediate species, which after releasing N2 gas forms a carbocation. Okay, so this is all about the carbocation. Now we are going to discuss about carbenes. So carbenes are organic ions which contains negatively charged carbon atoms are called as carbanions. It is a negatively charged carbon atom having 8 electrons. Here is the most important thing, that the carbanions are 8 electron species. So their octet is completely filled. So they act as a nucleophile. So carbenes act as a nucleophile. Generally, it undergoes sp3 hybridization. So geometry is trigonal pyramidal geometry, and bond angle between the bonded atoms is 109.28 degrees. So here you can see that this is a sp3 hybrid orbital containing electrons. So generation of carbanions. Here it also formed by the heterolytic cleavage of the covalent bond. So formation of the carbanions can be achieved by the following methods, which is hydrogen abstraction by strong base from carbon alpha to cyano, nitro or carbonyl groups. Okay, so first step is what? Abstraction of the hydrogen by strong base from the carbon alpha to cyano, nitro or carbonyl groups. So basically this is a functional group, your functional group, that is your nitro group, and the carbon next to the functional group is known as alpha carbon. So here is when a strong base is reacted with this species, the strong base will abstract hydrogen from this species, and abstraction of hydrogen gives negative charge to the carbon atom. So formation of carbanion takes place. Here you can see that this base abstract this hydrogen, and this hydrogen gives its electrons to carbon. So here it is formation of carbanion. Second is nucleophilic addition to alpha beta unsaturated species. So nucleophilic addition to alpha beta unsaturated species will also give carbanion. Then abstraction of terminal hydrogen from acetylene molecule. So acetylene molecule, here you can see that this hydrogen abstracted, and this abstracted hydrogen gives its electrons to carbon. So there is a formation of carbanium. So we have seen the formation of carbanions. Now we are going to discuss the stability of the carbanions. So there are various factors which affects the stability of the carbanions. Let's see one by one. The first factor is inductive effect. The stability of alkyl carbanions can be explained by the inductive effect. With increase in plus I effect, the stability will decrease. With increase in minus I effect, the stability will increase. Here you have to understand one thing, that the plus I or plus R groups are the electron donating groups. So the groups which have tendency to give electrons to the others are known as donating groups. Now you can see that the carbanion is already 8 electron species, so it doesn't have any need of the electrons. And you are going to attach it with the plus side donating groups, then it will lose its stability because it is electron rich species, and you are attaching it with the electron rich species. The electron rich will form unstable compound. So with increase in plus I effect, stability will decrease. With increase in minus I effect, the stability will increase. Now minus I effect means electron withdrawing effect, where the groups which are attached to the species withdraws electron from that species are known as minus I effect or minus R effect. That is electron withdrawing groups. So here you can here you know that the carbanions are electron rich species. If they are electron rich species and they are attached to the electron deficient species, they have tendency to give their electrons to the electron deficient species. So when there is an increase in minus I effect, the stability of the carboanion will increases. Greater the number of alkyl groups, that is plus I attached to the carbon atom bearing negative charge, lesser is the stability. It is reverse of that carbocation. In carbocations, the stability increases with increase in the number of plus I groups. Here, the stability will decrease if the plus I group increases, because their inductive effect increase negative charge and density on the carbon atom. Here you can see that the stability of carbanion. Here CH3 is more stable then this species, then this, and then this. Here you can see that here is no plus I effect giving substituent. Here is one CH3 group, here is two CH3 group, and here is three CH3 group. As you know that it is electron donating species. If they donate electrons to this negative charge, and this negative charge also contains electrons, so this species becomes unstable. Now second is effect of resonance. A carbanion is stabilized by resonance if double bond is located at alpha to the anionic carbon. Due to delocalization, negative charge diffuse over whole molecule and thus stability is increases. This explains the stability of allylic and benzylic carbanion. So in resonance what happens? If there is a double bond and negative charge, the negative charge will give electrons to the that species, and this double bond will shift here. There is a resonance, formation of resonance, and if any molecule in which resonance is possible, this molecule is stable. Third is electronegativity of carbanionic carbon. So the electronegativity depends on the percentage of S character. The stability is directly proportional to the electronegativity of carbanionic carbon, which is directly proportional to the percentage S character of carbanionic carbon. So how percentage S character is determined? So there are in organic chemistry basically three hybridization are most important. That is sp3, sp2, and sp hybridization. In sp3 there is a here you can see that in sp3 there is only 25% percentage is present. In sp2 there is 33%, and in sp hybridization it is 50%. So the percentage of S character increases, the electronegativity of the molecule also increases. Here you can see that the here you can see that here is sp3 hybridized carbon, which has less which is less stable than sp2 hybridized, which is less stable than sp hybridization. Why? Because this sp hybridized carbon or sp hybridization contains percentage S character, that is 50%, and if the percentage S character is more, the molecule is more electronegative, and electronegativity means the tendency to gain electrons from the species. So here is this is electron rich species, and if the percentage S character is more, this carbon will be electron deficient, and it has tendency to give electrons to that carbon. So there is the stabilization. Here you can understand that sp hybridization is more stable than sp2, and sp2 is more stable than sp3 hybridization. So it is all about carbanion. Next is benzyne. So what is benzyne? I will change the color of the pen. So benzene, what is benzene? Benzene has a strained triple bond. It cannot be isolated in this reaction, but is formed as a reactive intermediate. Here you can see that the structure of the benzene molecule. Okay, here you can see it is a strained triple bond. It is a strained triple bond which is cannot be isolated in this reaction, but it is formed as a reactive intermediate in this reaction. So aryl halides undergo substitution when treated with very strong base. So aryl halides when treated with strong base, they undergoes substitution reaction. So basically the compounds like benzene or aromatic compounds mostly use substitution reaction because they are already electron rich species. If the addition occurs, the electron density will decrease and the aromaticity will get lost. And if the compound lost its aromaticity, it will lose its stability. So aromatic compounds are more stable than non-aromatic, anti-aromatic and non-aromatic compounds. So aromaticity will be retain. So for the retention of aromaticity, aromatic compounds always gives nucleophilic substitution reactions, okay, or substitution reaction. Here, when aryl halides undergo substitution by treated with very strong bases. Here you can see that this is benzyl chloride. Okay, this benzyl chloride when reacted with strong base. Here you can see that this is a strong base in presence of ammonia. It is used as a solvent. Here you can see that this is K plus and NH2 minus. It is NH2 minus. So it is not working properly. Here this K will possess positive charge and N possess negative charge. Here is you can see that this chlorine is replaced by the NH2 group. So what is the mechanism? Here you can see that this K plus and the NH2 minus. This NH2 minus will abstract the hydrogen from the benzene ring and this hydrogen will give its electron to the benzene ring. After giving electrons to the benzene ring, this chlorine will get removed. So here you can see that here is attack of the abstraction of the hydrogen by this group and the hydrogen gives its electrons to benzene ring and the chlorine will get removed. Here you can see that formation of benzyne takes place. Now the compound form is in this step is called benzynes. Then next step, that is step 2. Here in our reaction NH2 minus is present. This NH2 minus will attack on the benzyne. So after attacking on the benzyne, this one of the bond of this triple bond will get will give its electron here. That is here it will be negative charge and here NH2 group is attached. Engelstein is relieved. The 2sp hybridizing carbon in benzene becomes sp2 hybridized in resulting anion. Here is formation of anion. So basically what happens, the benzene is a species. This is a benzene. It is your benzene. Now it is your base. This base will attack on the triple bond. This triple bond will give its electron to the adjacent carbon and formation of the anion. Here you can see that formation of anion. So now this anion will abstract hydrogen from the reaction and formation of this group is okay. That is the benzene mechanism. Now next is free radical. So free radical is a reactive intermediate with a single unpaired electron. It is a reactive intermediate with single unpaired electron formed by homolysis of covalent bond. Here up above the formation of the free radical is because of the homolysis of covalent bond. These species are generally short-lived. These species are generally short-lived, extremely short-lived in a solution, but can have longer lifetime in crystal lattices of other molecules. Example, these are the radicals. Free radicals are atoms or groups of atoms having an odd or single unpaired electron. A radical contains an atom that does not have an octet of electron, making it reactive and unstable. So here you can see that it is a AB molecule. Here is the homolytic cleavage of the bond. Here one electron goes to A and one electron goes to B. So there is formation of radical A and B. These are the radicals. So free radical has the following characteristics features that free radicals are electron deficient species. They are usually uncharged. They contains odd number of electrons. The electrons must be one or odd number of electrons. The alkyl radical have 7 electrons around the carbon bearing a radical character. In methyl radical or other alkyl radicals, the radical center is trivalent and trigonally hybridized. The carbon is sp2 hybridized. Here you can see that hybridization of carbocation and free radical is same. That is your sp2 hybridized. That is its structure is planar structure. Now stability of the free radicals. The stability of the free radicals also depends on the inductive effect. It is same as carbocations. Primary radical is less stable than secondary, and secondary radical is less stable than tertiary, and methyl radical is less stable than primary. Why? Because here also inductive effects work. That is, electron donating groups are present on the free radical, it will make the radical more stable, and electron withdrawing groups are there, then the radical becomes less stable. Free radicals are more stable if they are highly substituted. Here you can see that tertiary is more stable than secondary, secondary is more stable than primary, and primary is more stable than methyl radical. Then resonance in allyl free radicals. So the resonance will also stabilize the radicals. Resonance in benzyl free radicals. Okay, here you can see that this will give electron here, and this 1 minute. Here you can see that this will give one electron here, and this double bond will give one electron here and one electron here. So here is formation of or resonance of the radicals. Here you can see that radical is here, here radical is here, here radical is here. So radical is resonating in the benzyl ring, so it is more stable. Then next is carbene. So carbenes are highly reactive species having a lifetime less than 1 second. These are defined as neutral divalent carbon species in which the carbon has 6 electrons in valence orbital, 4 covalent bonded electrons and 2 non-bonded electrons. So it is also 6 electron species, but 4 covalent bonded electrons and 2 non-bonded electrons. Here it is the structure of the carbene, methylene. It has 6 electrons. It is neutral species, incomplete octet, electron deficient species, act as a electrophile, highly unstable, very short lived species. So types of carbene. There are two types of carbene, that is singlet carbene and triplet carbene. Here we will discuss how. The non-bonded electrons are paired and are in anti-parallel spin. Here you can see that this is the p orbital, empty p orbital, empty p orbital. Here you can see that this orbital is paired. Here one electron is here and one electron is here. That is paired with anti-parallel spin. Okay, this is non-bonded electrons are paired and in are anti-parallel spin. Shape is trigonal. Violates Hund's rule. Spin state is 2s plus 1. Okay, it is also have hybridization sp2. Here you can see the structure. So here the non-bonded electrons are present in a same orbital with anti-parallel spin. So therefore this called as singlet triplet. Singlet carbene. Next is triplet carbene. Next is triplet carbene. The non-bonding electrodes in the triplet carbene occupy different orbital and has opposite spin. Here you can see that here is one electron and here is one electron with the opposite spin. Okay, and has opposite spin. Shape is linear, paramagnetic. Hund's rule it follows Hund's rule. Here you can see that spin state is 3 and here you can see that spin state is 1. So therefore it is singlet carbene and it is triplet carbene. Its hybridization is sp hybridized. So there are two types of carbene, that is singlet carbene and triplet carbene. It is the classification is based on the non-bonded electron pairs are paired and anti-parallel spin, or the non-bonded electrons are paired or sorry different orbits मध्ये they are present in different orbits. Okay. Then formation of carbene. So where there are various reactions which involves formation of carbene. First is from aliphatic diazo compounds. The diazo compounds means compounds containing N2 group. Okay, compounds containing N2 group. From aliphatic diazo compounds can be decomposed either photolytically or thermally to generate carbene. Here you can see that it is diazo propane, where photolytic Q H nu is that is photochemical reaction. Here the formation of dimethyl carbene. Formation of dimethyl carbene. Second, from ketenes. Those ketenes are the molecules which carbon is bonded doubly to oxygen or doubly to its adjacent carbon. So here ketenes can be decomposed thermally into carbene. From epoxides, photolytic decomposition of epoxide generates carbenes. Here you can see that epoxide. So cyclic ethers are known as epoxides. Here is the formation of carbene. From diazirenes, decomposition of diazirenes generates carbene. Now the factor that is stability of the carbenes. So carbenes, triplet carbenes are more stable than singlet carbenes because with two electrons in different orbitals, there is a less electrostatic repulsion than both are in same orbital. So you know that in triplet carbene or in triplet carbene, the both the electrons are present in different orbitals. So the electrons are present in different orbitals, then there is a less electrostatic repulsion between the both the electrons that is present in the same orbital. So triplet carbene is more stable than singlet carbene. In halogen substituted carbene, the singlet carbenes are more stable than triplet carbene due to overlap of their lone pair of electrons to the empty p orbital, thereby stabilizing the singlet carbene. So when the carbene is substituted by halogen, the triplet carbene is less stable than singlet carbene, because in singlet carbene the lone pair of the halogen atoms will overlap with the empty p orbital, therefore stabilizing the singlet carbene. Third, the order of stability of halogen substituted carbene. CF2 is more stable than CCl2, which is more stable than CBr2. This is due to bond length, which provides more extensive lateral overlap of the respective p orbitals. So, size of the halogen increases, the stability of the carbene decreases. Next intermediate is nitrene. Nitrene is the nitrogen analog of carbene. These are defined as neutral monovalent nitrogen species in which nitrogen has 6 electrons in its valence orbital. So this is the structure of the nitrene species. Characteristics of nitrene: it has 6 electron and electron deficient. They are regarded as electrophile or Lewis acid. They are short-lived and highly reactive due to their strong tendency to accept 2 or more electrons in order to complete its octet. So types of nitrene, again it is similar to the carbene, singlet nitrene and triplet nitrene. In singlet nitrene, the 4 non-bonding electrons on nitrogen are present as 2 pairs having anti-parallel spin and has no magnetic moment. They are sp2 hybridized. Here you can see that this is singlet nitrene. Here you can see that these 2 electrons are present in same orbital with anti-parallel spin. These 2 electrons are present in the same orbit with anti-parallel spin. Now triplet nitrene. In triplet nitrene, the 4 non-bonding electrons are present on the nitrogen in the form of 1 lone pair and 2 unpaired electrons having parallel spin and has magnetic moment. Here you can see that these electrons are present in different orbits with parallel spin, making it paramagnetic. So formation of nitrene from elimination. Okay, so when here formation of nitrene by elimination reaction. Here you sorry. So here you can see that this when base is added, this base abstract hydrogen and hydrogen gives its electrons to the nitrogen. Their formation of nitrene. It is an intermediate with negative charge. This negative charge will give its electron to nitrogen, and this leaving group will live here. Formation of nitrene. From azides, thermal or photolysis photolysis decomposition of azides gives nitrenes. Here you can see that formation of nitrene from sulfilamine, pyrolysis of sulfilamines generates nitrene. Here you can see that formation of nitrene. Then next intermediate is ketene. So ketene is a molecule that is highly electrophilic at the carbon atom, bonded with heteroatom due to sp character. So here you can see that this is a ketene where carbon is attached to the heteroatom, and there is another carbon with double bonds. Here is double bond and here is double bond. So ketenes can be formed with different heteroatoms bonded to the sp carbon atoms such as oxygen, sulfur or selenium, respectively called as ketenes, thioketenes and selenoketenes. Okay. So synthesis of ketenes. So ethanol is produced on a commercial scale by thermal dehydration of acetic acid substituted by ketenes can be prepared from acyl chloride by elimination reaction in which HCl is lost. Here you can see that this is a acyl chloride. This is acyl chloride. When base is added to that, the base will abstract hydrogen from the acyl chloride, and this hydrogen will give its electron to the carbon atom. Okay, the bond between carbon. And here is the formation of double bond. This double bond formation takes place, and this chlorine group will be get departed from the species. And here is formation of ketene. In this reaction, a base is usually triethylamine removes the acidic proton alpha to the carbonyl group, inducing the formation of carbon-carbon double bond and the loss of chloride ion. So applications of ketenes can be: ketenes are strong acylating agents. They react with carboxylic acid to form carboxylic acid anhydrous. Here you can see that this is a ketene and this is carboxylic acid. So this carboxylic acid, what happens? Here you can see that the formation of carboxylic acids anhydrides. Now with alcohols gives carboxylic acid esters. With amines it gives amides. Here is the Tilsel reaction, that is cycloaddition reaction, in which this nitrogen will attack here. This double bond will also attack here. Formation of cyclic compound, that is cycloaddition reaction takes place. 1 minute. It is a 2+2 cycloaddition reaction. It is 2+2 cycloaddition in which formation of cyclic compound takes place. So this is the applications of ketenes. So it is all about the intermediates that we have studied so far. So here you can see that we have discussed carbocations, carbanions, carbenes, free radicals and nitrenes. Here carbocations are electron deficient species because it has only 6 electrons in its valence shell. Okay, it is an electron deficient species. It is sp2 hybridized species that is planar in geometry. Okay, carbanions are electron rich species because 8 electrons in its outermost shell. It is a sp3 hybridized species. Then carbenes, free radicals and nitrenes. So all these are electron deficient species. Okay, all these are electron deficient species. So that's all about the carbon reactive intermediates involving carbon. Thank you.